call is now being recorded.
Good morning, everyone. So, let us start today's discussion. Hope you're all doing good. Had a happy Diwali, and I'm waiting for my sweets from North India to be delivered, or from anywhere to be delivered at home or to the college. Right? Hope you have dispatched them. Okay. So, today's discussion is a very important topic, not just one topic. Whatever is going to be discussed is uh, amalgamation or a combination of whatever we have learned uh, till now. That important is today's discussion because it combines all the concepts that you have learned and it is being applied. Okay, so to start with, let us set the background. We were discussing asynchronous counters using T flip flops. T flip flops are toggle flip flops. A toggle flip flop is the one for which the excitation table is like this. If you are in a state of 0, when t is equal to 0, it will go to state, it will remain in state 0 itself. Whereas if t equal to 1, if it was in a state 0, it will go to state 1. If it was in state 1, it will go to state 0. This is how a t flip flop behaves. And if you look at the table of a JK flip flop, interestingly, you will see that a JK, a JK flip flop, we'll see the detailed diagram. A JK flip flop, we have written the reduced table. So in the reduced table, you saw that if j is 1 and k is 0, irrespective of the present state, the new state will be 1, or in other words, it will set. Similarly, if j is 0 and k is 1, irrespective of the present state, it will go to the reset condition. So these two are known to us. J equal to 1 will set, and if k equal to 1, it will reset the JK flip flop. But look at these two, 0, 0. If j and k are both 0, okay, then whatever is the present state, that will continue. If j and k are both 1, whatever is the present state, its complement will be the new state. So if j and k are equal, if they are unequal, it depending on whichever is high, output will be either set or reset. But if they are equal, then this behavior, that if it is 0, it will be present state itself. If it is 1, it will be the next state, the complement of the present state. That is very much similar to the behavior of the t, because the t, this is t equal to 0, and this is also t equal to 0, and this is the case where t equal to 1. So when t is equal to 1, it's complementing, and t equal to 0, it is remaining without any change, isn't it? No change. 0, 0, no change. 1, 1, no change. So with t equal to 0, there is no change. With t equal to 1, there is change, complementing. Which means if I have a JK flip-flop with me, and if I just make them both have their j and k equal, then that input I can call as a t. Yes or no? Okay, which means if I have with me a JK flip flop, I can convert it into a T flip flop, and this effectively I can say I can draw like this. I can just say that I have a T flip flop. This is equivalent to this. Do you agree? What did I do? Internally, I have a JK flip flop, and its J and K I shorted, I connected them, tied them together, and the tied input is what I call as the T input. So effectively, I can convert a JK flip flop to a T flip. I tell you this because in lab, when you try to do experiments practically, IC which we have in the lab is 7476. This is a JK flip flop. Whereas we don't have any T flip flops. No T flip flops are available commercially. Only half of the notebook is visible. Is that better now? Hello? Or maybe I had kept the slides also open. Yeah, is this okay now? Can you see now? Both the entire notebook? I forgot to ask this question at the beginning. Is it visible? Both?
Yes, ma'am.
Okay, so what I maybe you didn't see this, is it? You didn't see what I was writing here. Is that so? Or did you see this discussion? You saw this? What we said?
Yes, ma'am.
How we interpret that the JK can be is becoming a T flip flop. You saw that?
Yes, ma'am.
Okay. So now what I just concluded is that with internally, if you have it inside, you have a JK flip flop. But now by shorting the JK input, I converted it into a T flip flop. Why we say this is because 7476 is the JK flip flop available with us. It's a dual JK, which means that inside one chip you have two such flip flops. Okay? Dual JK. So dual JK flip flop IC, but there is no T flip flop available commercially. So what will I do with all these circuits? I've been discussing all these circuits with T flip flops. So practically, how will I do it? Tell me, how will I do it? How will I do the circuit practically in the lab? I will have to, I will have to, I will have to take a, yes, I will have to take a JK flip flop 7476, find out its J and K pins and connect them together and connect the point to a high voltage, 5 volt. Is that clear to you? Or in other words, this circuit, when I draw it, instead of drawing like this, I would have to practically, I will have to wire it like this. I will have to take a J and K, connect a wire between them and connect that wire to VCC. So that this is now equivalent to what? This is now equivalent to a T flip-flop whose T is connected to VCC. Is that clear? So all these T flip-flops, when you're doing it practically in the circuit verse, you have this. It's only simulation, right? But lab, when you do it, you don't have T flip-flops in the lab. You have only JK flip-flops, and you have another kind of flip-flops called as D flip-flops. So if you want to implement some circuit using T, then this is the only way out. I hope it is clear. Is that clear enough? So this is an important takeaway. Huh? Practically, we don't have JK flip-flop. Sorry, we don't have T flip-flop. We have to convert our JK into T. And there is a systematic procedure to convert any flip-flop to any other flip-flop. Okay? Any flip-flop can be converted to any other flip-flop. That is, if you have a JK, if I want to make it as a T, this is the way. And if I have a JK, if I want to convert it into a D, there is a methodology. So we will see conversion of flip-flops. I have recorded a video on that, so I'll post it this week. You can see the systematic procedure. which can be used to convert any flip-flop to some other flip-flop. So this I just said, it is quite obvious from the observation itself, but there is a systematic way in which you can prove that if you have a JK flip-flop, keeping its J equal to K, then I can make it a T, and that will be my T. Okay, I can show this through a design procedure, systematic procedure. So that I'll hold for the time being. So that was just a starting. So now that all of you are here, what we Muhammad Hashir, why did you start presenting? Okay, is the full book visible now, all of you? Okay, so in the last class, what we discussed is we analyzed the asynchronous.
Hello, ma'am. A lot of students are actually facing issue.
What issue?
Okay, right now the presentation came. Till now the presentation was not visible.
അത് ഇടയ്ക്ക്
Everywhere,
ഹാഷിറിന്റെ പ്രസന്റേഷൻ വന്നു പോയി
no. Till now it was actually blank. Everybody was watching through directly through the cam. ഇപ്പോ ശരിയായിട്ടുണ്ട്.
എനിക്ക് കാണാതായപ്പോഴാണ് ഞാൻ ജസ്റ്റ് നോക്കിയപ്പോഴാണ് അതിന്റെ കൈ തട്ടി പ്രസന്റ് ആയി പോയത്. ഇപ്പൊ കാണാം.
Okay.
Now it's visible, ma'am.
Okay. So in the last class, what we discussed was, in the last two classes, we have been discussing this. We took the flip-flops, we do its timing diagram, hope you remember this. And then I said the previous flip-flops is connected as the clock for the second flip-flop. So this is the LSB flip-flop, this is the next one, this is the MSB flip-flop. And then we assume that transitions are going to happen for every clock. First flip-flop will toggle for every clock of the incoming signal, every falling edge is toggle. And the second flip-flop, since Q is connected, whenever there is a fall on the Q of this flip-flop, this will toggle, and it goes like this. So it looks as though the effect of this clock is rippling through the different sections. Effect of the incoming clock is rippling through the different sections, and hence these kind of counters have two names. One, they're called as asynchronous because the different clock inputs are not getting signal simultaneously from the external clock. So in that sense, we called it as an asynchronous counter. And then another name given to this kind of counter is the ripple counter, RIPPLE, ripple counter, because it looks as though if apply a signal here, this will go through this, cause a change here, and it is this change that is going to appear as the clock here. So you can say that the effect of clock has to ripple through the stages. So the more the number of stages, more the number of ripples would be. Ripple would be. Hope that concept is also clear. I'm going to start from here, this point. And the other concept which we discussed is how to reduce the maximum modulus. When you have three flip-flops, you have a maximum modulus given by 2 raised to 3.
Excuse me, ma'am. Ma'am, the presentation is for everyone. It's like frozen.
ഹലോ മാം, അതിൽ സ്ക്രീന് റൊട്ടേറ്റ് ചെയ്താൽ ഫുൾ സ്ക്രീനിൽ കാണാം. എനിക്ക് ആദ്യം ഞാൻ റൊട്ടേറ്റ് ചെയ്യാതെ നോക്കിയപ്പോൾ മാമിൻ്റെ ബുക്ക് പകുതി കണ്ടിട്ടുണ്ടായിരുന്നുള്ളൂ. ഞാൻ സ്ക്രീൻ റൊട്ടേറ്റ് ചെയ്തപ്പോൾ ഫുള്ളായിട്ട് കണ്ടു. ഫുള്ളായിട്ട് കുറച്ച് അങ്ങനെ പ്രശ്നമുണ്ട്.
എൻ്റെ സ്ക്രീനോ? നിങ്ങളുടെ സ്ക്രീൻ?
ഞാൻ ഉദ്ദേശിച്ച മാമിൻ്റെ ബുക്ക് കാണുന്ന ആ ഒരു ഇതാണ്.
ഇതുവരെ ഇല്ലാത്തിരുന്നൊരു പ്രശ്നമാണ്. ഒരു മിനിറ്റ് ഞാൻ നോക്കട്ടെ. Is that better now?
Ma'am, are you presenting?
Yeah. Maybe it's just coming up. Better?
Yeah, presentation is visible, ma'am. Better.
What about now?
It's good now. It's visible.
Both the slide and the
Both.
no.
Yes, ma'am. Both the PPT and the book is visible right now.
Okay, here we go. Okay, so what we please let me know now, because I have not kept my second lap up to see whether everything's fine. So what we discussed is that for every falling edge, there will be clock rippling through the different stages. So that is why we call it as a ripple counter. Now today, and then we also saw how we can convert from the maximum modulus to a reduced modulus. By using an extra circuit, you can utilize the clear facility of the flip-flop and cause an asynchronous clearing. At the point, asynchronous clearing can be caused, asynchronous resetting can be done at the point at which you want to stop counting. So if you want to count from 0 to 5, at 6, you cause a reset. You detect 6 and cause a reset. So if you want to count from 0 to 10, what should you do? If you want to count from 0 to 10, you have to take a flip-flop arrangement where you have 4 flip-flops, correct? Because 10 you can get only if you have a counter with 16 modulus. That is, you have to take a counter with the next highest modulus, which is a power of 2. Okay, so take a mode 16 counter, make it count 10 state, and for the 11th state, make it switch. So 10 states in Warimbo, you have to get 0 to 9. Isn't it? When I want a mode 10, I should count from 0 to 9. So choose a mode 16 counter basic arrangement like this with 4 flip-flops. So that is the one you have to choose. And decoder circuit, this kind of a decoding, you do for which count? What should you detect? You have to go from 0 to 9. So the next state after 9, what will come is 1010. So you should force this 1010 to go to clearing, resetting, which means if I modify this circuit, I'll have to just plug in one more T flip-flop, connect its T to VCC. The Q of this will have to be connected as the Q for this.
ബിനു മാം
Ah,
മാം 2 പേജിന്റെ പൈതി കാണുള്ളൂ.
ഇപ്പോഴും
ആ
രണ്ട്
പേഴ്സണലി എന്റെ സൈഡില് കുഴപ്പമില്ല.
രണ്ട് പേജിന്റെ പകുതി പകുതിയോ?
ലെഫ്റ്റ് സൈഡിന്റെ ആ 13, 11, 20, 20 അത് കാണാം. സോറി 26
ആനന്ദ് ഫോൺ ഒന്ന് തിരിച്ചു പിടിച്ചു നോക്കിയേ.
ഇപ്പൊ ഓക്കെ.
അങ്ങനെ പിടിച്ച് വേണം കാണാൻ. Okay, so mode 10 count if you want, you have to count from 0 to 9. So it is 1 0 1 0 which you have to cause a reset with. So what we do, we instead of this, you have to think of a circuit, any circuit. Let us use a NAND gate. So if I use one, I want to cause a 1 0 1 0 reset, isn't it? 1 0 is on Q3, on Q2, on Q1, on Q0. So Q3, Q2, Q1, Q0, 1 0 1 0, when it comes, it should cause this reset, and this I'll connect to all the resets including this fellow. Okay, ignore this. This is last day circuit. So you take a NAND gate, you connect it such a way that when 1 0 1 0 comes, you get a 0 here. How will you ensure that? You can connect Q3 directly, take Q2 and invert it. Okay, invert it and connect it here. Take Q3, take Q0 and invert it and connect as a fourth input for the NAND gate. So use this 4-input NAND gate. Its output you can connect to all the clears, in which case your counter will go from 0 to 9. On the next clock it will go to 1 0 1 0, but it will be forced to go to 0 0 0 0 and start all over again. That is the discussion which we have had the other day. We had a detailed discussion of that, and we all know flip-flops do give us Q and Q bar output, so you don't need this inverter. Instead, Q3 you can take directly from here, the Q3 output, and here the flip-flop will give you a Q3 bar. So take this connection and put it as if you need Q3 bar. And similarly, you have Q2 bar here. This is your Q2 bar. So take Q2 bar and give us the input for this. So you don't need those inverters. All you need is an extra NAND gate. So to the input of the NAND gate, you apply the proper Qs. Apply appropriate Q to the input of the NAND gate and feed it back as the clear. Okay, so that will take you to modulus 9. So the takeaway here is that you should be using a circuit which can give a counting of maximum modulus which is greater than what you want. And how do you choose it? Choose it so that the maximum modulus the circuit gives is that value which is the next power of 2. So if you want mode 10, the next power of 2 is 16. So choose a mod 16 normal counter, tweak it like this. Tweak it like this and use the clear facility, and you can make it count from 0 to 9. When I count from 0 to 9, there is a special name given to that counter because it is 0 to 9. It's called as a decade counter. So what we just discussed is asynchronous decade counter, decade up counter. This is what we just discussed. Asynchronous decade up counter is this. Okay. Okay, so this was just a recap. So now let us move to today's discussion. I was setting a platform. I'll not be repeating asynchronous counters anymore. You have to catch up the details and understand the various intricacies. Okay, now let me take you through another discussion. I'm just drawing two T flip-flops. I hope you're drawing with me. Both of them are connected to 1. Let me call this as T0, this is T1. There is an external clock which is connected here. Please note the symbol. I drew without a bubble. I drew without a bubble. Now this flip-flop has got a Q and a Q bar, and this also has got a Q and a Q bar. following the same convention, let us call it as Q1, Q1 bar. This is Q0, Q0 bar. All set. Now, imagine that the flip-flop has got clear. Both clears are available to you. Okay, so now the twist is, first is here, the clock. So this is also something like this. What does it mean? A simple triangle without a bubble indicates what? Positive clock, positive edge triggered. Okay, so here is the twist. I'm not connecting Q0, I'm connecting Q0 bar as the clock to this. And now let us observe what will come out as your Q1 and Q0. And out of this, which is the LSB, this flip-flop output is the LSB. There is no magic in it. You just have to apply the concepts which you have learned. So let us start by drawing the timing diagram. What is the horizontal axis for a timing diagram? What is it that you're drawing? What is this axis? Good, it's time. Don't be confused about this. It's time. And what is the vertical axis? In the vertical axis, you're showing the voltage. Since it is a binary signal, it is either a 0 or a 1. Digital 0 or digital 1, which in terms of voltage, it will be either a 0 volt or a 5 volt or a 0 volt or a minus 5 volt, depending on what kind of logic you're following. Okay, so this, let me call it as the external clock, this clock. So can somebody tell me what kind of counter is this? Asynchronous or synchronous? Asynchronous only, because the clock, the incoming clock is applied only to the first flip-flop. The second flip-flop is getting clocked from the first flip-flop's output. So it is asynchronous only. But the twist here is that they're going to be triggered on the positive edge. So these are the edges of importance to us in this example. Okay, these are the edges at which transitions will happen in the circuit. So now let us draw the transitions which can happen on Q0. I'm drawing Q0. Okay, let us draw the transitions that can happen on Q0. Since T is a 1, for every rising edge of the clock coming to it, Q0 will toggle. And let us start with the assumption that we have initially made it 0. So initial value, let us assume that initial value 0. Now you all know how to make the initial value 0. What should I do? Make the clear active 0 for a small duration. That will cause both the flip-flops to get clear, and then you switch on the clock. Okay, then you switch on the clock. Now what will happen? On the first rising edge, Q will have to undergo a toggle, and it will remain in that high condition till the next rising edge. Toggle, toggle, and it goes like this. Great. What about Q1? What about Q1? Let us again assume that Q1 is initially at a 0 value. What will happen to Q1? On the first rising edge, there was a toggle in Q0 from 0 to 1, isn't it? A toggle was there on Q0 from 0 to 1. So what is happening on Q0 bar? What is happening on Q0 bar then? If Q0 is happening like this, then initially Q0 bar is a high, correct? So what will happen when Q0 goes high? Q0 bar would have gone, Q0 bar would have gone low, correct? So what you see on Q0 bar is just opposite of what you see on, or just inverted of what you see on Q1. So this is what you would see on Q0 bar. Okay. So the question is, when the first clock comes, Q0 bar toggle. And since you have connected, sorry, Q0 and Q0 bar, both of them toggle to their opposite states. But since you have connected Q0 bar as the input clock for the next stage, and since the next stage is a positive edge triggered stage, will it respond to the first clock? Let us call this as clock 1, 2, 3, 4, 5, and so on. So will this first clock appearing here cause a toggle here? Is it capable of causing a toggle there on Q1? No, isn't it? Because it is this edge that can cause the first toggle on the second flip-flop. Yes. So if I try to draw the condition of Q1, and if I say that Q1 is initially 0, then Q1 will have to remain initially 0 till it gets a valid clock, which is here. And then it toggles. Is that clear to you? It toggles for high on high going edge on Q0 bar. Okay, then it goes like this. Where is the next high? Here is the next high on Q0 bar. So that is where it toggles again. Where is the next high? Here is the next high. So it toggles again, and this is how it behaves. Okay, so there is no magic here. It is just a question of understanding the working and then just interpreting it. Now let us try to write down the conditions, that is the value of Q1 and Q0. I'm going to write Q1, Q0 as a table now. So let us do it. Let us start with 0, 0, which is the initial condition. So in the first interval, what is the status of Q1 and Q0? In the first interval, what is the status of Q1 and Q0? This is my Q1 and this is my Q0. Okay, a blue one the Q0 bar. So this is my Q1 and this is my Q0. What is the value? What is the value? Q1, Q0. After Q0, 0, 0, what is the value? Q1 is a 0 and Q0 is a 1. Q1 is a 0 and Q0 is a 1. I wrote it here. Okay, let's move on to the next period, the next change. So it is 0 here and a 1 there. Next, it is 1 here and a 0 there, right? So it is 1, 0. Next, it's 1, 1. Are you clear? What happens next? Q1 becomes a 0, Q0 also becomes a 0. It goes back to 0, correct? It goes back to 0. So what is the modulus now? Mode 4. What is it doing? Up counting or down counting? Correct. Up counting. Synchronous or asynchronous? Asynchronous. Asynchronous. But is the circuit same as the previous circuit which we discussed? Is the circuit same as the previous circuit which we discussed? No. What is the difference? What is the difference of this circuit from the previous circuit? What was the flip-flop in the previous circuit? There also it was a T flip-flop, but it was a negative edge triggered T flip-flop. What is it flip-flop here? We are using a positive edge triggered flip-flop. So the component is different, correct? The component used is different. What is the circuit difference? What difference did you make in the circuit? Yes, Q bar was connected to clock. Q bar to clock. There in the previous circuit, you connected what to clock? Q. Every Q was connected to the subsequent clock. Every Q was connected to the subsequent clock. So if I can put one more flip-flop here and make a similar connection, what do you think you will get? If I put one more T flip-flop here and make a similar connection, this Q bar will be connected to that flip-flop's clock. What do you think you will get? You get a higher modulus up counter, right? Yes, mode 8. Yes, so what I just wanted to convey is, to get asynchronous counters or to implement asynchronous up counting, you have two options. One option is use a negative clock flip-flop, negative edge triggered flip-flop, okay, negative edge triggered flip-flop, cascade Q to clock. Is that clear? To get an asynchronous up counter, use negative edge triggered flip-flops. Of course, you have to use only T flip-flop. Huh? So use that. That's very, very important. Asynchronous counters, we use only the toggle functionality. Okay, so use a negative edge triggered flip-flop and connect cascade Q to the clock. What is the second method? Use positive edge triggered flip-flop. Use positive edge triggered flip-flop and cascade what? Cascade Q bar to clock. Is this clear to you? If it is clear, tell me, how can I make an asynchronous down counter? Okay, take a negative edge triggered flip-flop, negative edge triggered, and then yes, Tom, good. Cascade, cascade, Q bar to clocks. So when I say cascade, I mean that for the first stage I use the first Q bar, second stage I use the second Q bar, and so on. Okay, so that's the meaning, cascade, cascade Q bar to clock. Is this understood? Or do we have a second option? What is the second option? What is the second option? Can I do something with a positive edge triggered flip-flop? If my circuit is if my flip-flop is a positive edge triggered flip-flop, how will I do that? Yes, use positive edge triggered flip-flop and then cascade Q to clock. So I hope this similarity or symmetry or there is a pattern, right? I hope this pattern is clear to you. Think over this. Okay, think over this. Now, let me ask you a very silly question. Very silly question. We have been taking Q bar as the output, right? For this counter, we looked at it as if it is an up counter, and we took Q bar as the output to say that it is an up counter. What will be the output if I look at Q1 bar and Q0 bar instead of Q1 and Q0? That is, I decide to take this value and this value as my outputs. So suppose I'm connecting these to my LEDs and looking there. What do you think you will see? In other words, my question is, what is the respective Q1 bar and Q0 bar? When Q1 and Q0 is going like this, what is the behavior on Q1 bar and Q0 bar? That is an interesting behavior. What is the first, when Q1 and Q0 is 0, 0, what do you think Q1 bar and Q0 bar will look like? Yes. So just imagine, suppose you have connected two LEDs here and two LEDs here. Initially, these two LEDs will be off and these two LEDs will be on. Do you agree? Yes or no? Yes. Now, on applying the first clock, out of these two LEDs, one of them will be off and the other will be on, isn't it? It will be this will be on and this will remain off, correct? Or in other words, I'll be getting 0, 1. So at that time, if you look on this LEDs, these left side LEDs, what do you think they will show you? If it is 0, 1 there, it has to be 1, 0 here, right? The ulta, the opposite. Similarly, when on the next clock, when this happens, you will get 0, 1, correct? On Q1, Q1 bar. And the last clock, when the Q0, Q1 is at 1, 1, you would see 0, 0 here. Great. Now look at the sequence that you see on Q1, Q1 bar, Q0 bar. Look at the sequence. How does it go? 3, this sequence. If I look at the decimal equivalent of this sequence, it's going like 3, 2, 1, 0, back to 3. So what is the takeaway? 3, 2, 1, 0. Yes. So what is the takeaway? Then 3. Yes. What is the takeaway? What is the takeaway? Do you agree that this is a down counter? Yes. Do you agree that this is an asynchronous down counter? Yes. So the takeaway is the same circuit. If you take outputs from here, you can get up counting. And if you take outputs from the respective Q bars, you'll get down counting. That is also possible. Write it down in your own words what you understood. A single circuit. So whether you take outputs from Q and look at the value, or whether you take outputs from the Q bar and look at the value, you have one side you have up counting in progress and the other side you have down counting in progress. So if I just decide to connect LEDs or maybe displays, suppose you have seen 7-segment displays, right? You have seen displays like this on your calculator, on petrol pumps, etc. You might have seen displays like this which glow up in red color. Yes. Now suppose I have such a circuit. This circuit, suppose I have. So, and what is the connection? The same circuit. But then This is my Q0 and this is my Q1, and this is my Q1 bar and this is my Q0 bar. Okay, now imagine that I took this and connected it to the first segment. I took this and connected it to another segment. Okay, so this segment, if you give 0 0, this segment will show a 0. If you give 0 1, that is, if the value here it is 0 1, it will show 1. If it is 1 0, it can show 2. If it is 1 1, it will show what? 3. Okay, so suppose I am watching this output display. Okay, so this is connected here and this is connected here. Suppose I am watching this output on the screen. This output I am watching. Tell me what are the numbers that I'll see on the screen and how many different numbers will I see? For every clock, this is the clock. Every connection, everything is the same. This is Q bar, it's the same circuit. Q bar is connected here. So you have just understood that this is going to count up, correct? So this side is counting up and this side is counting low on every clock. If you have understood the concept, tell me what will you see here on the first clock? First clock, what will you see? This is connected to Q and this is connected to Q bar. So what will you see here on the first clock? Let us say we have not started. We have just initialized it. So what will you see here? Do you agree? Do you all agree that you will see a 0 here? What do you see here? Only 2 of you understood? If it on the first clock it is 3, isn't it? So this display will show 3, correct? Yes or no? Now in the first clock, what will happen? This will show display like 1, and what will be the display here? It will show display 2. Yes, next clock. Great, next clock. Next clock. Next clock. Fourth clock. Interesting, isn't it? Interesting, isn't it? Yes or no? Yes. So in your notebook, open a fresh page. Take a fresh page in your notebook. Okay, a fresh page. There are more discussions coming about. On a fresh page, just write down the same kind of sequence had it been a 3-bit arrangement. 3-bit money, you'll have one more flip-flop. So in your notebook, on a fresh page, write question number 1 and just write 3-bit arrangement sequence. Write that, and below that you write down all these displays, what you see on the 2. So when it is a 3-bit arrangement, you will have one more display, correct? You will have a third display. I'm sorry, you will not have a third display. I'm sorry, you will have a third bit come into it. I'm so sorry. When you have a 3-bit arrangement, this is Q. So all these are going to go into this, and all the Q, this is Q2 and this is Q2 bar. All the Q2 bar will go into the first one. All the Q bars will go into the second one. So you will have only 2 displays, but the counting here will progress for 8 states. So based on that, write down the pattern that you are likely to see. I'll give you 1 minute for that. You don't have to draw the circuit and all. Just write down the pattern. To start with, I will give you the clue. Start with the first. Here it will be a 0, and here it will be 7. Because it's going to be, if it is 0, it means it is 0 0 0, which means here the Q bars will be 1 1 1, and 1 1 1 is 7. So I want you to write down the remaining values. in 1 minute. Shubham, write it down in your notebook. Don't put it in the chat. Please write it down in the notebook. And as I told you in your WhatsApp group, today at the end of the class, you will have to scan and upload your notebook. This page. A couple of pages more. So this is the first page. Finish it. I'm waiting. One more minute. Those who finished can go grab a cup of coffee and come back. Those who finished, grab a cup of coffee, come back. Okay, done. Done. Don't try to copy here. There is all flexibility for you to copy or ask somebody and write, but then I want you to think and write. Okay, now let's move on. So far, everything was perfect. There was a clock coming, and immediately the clock caused a transition. I repeat, there was a clock, and immediately the clock created a transition on Q0. So that's what we drew. The moment the clock comes, the same moment it goes high. But do you think this will happen in the same instant simultaneously? Can this transition happen without any delay? Can this circuit respond with zero response time? Can any circuit for that matter respond with zero response time? No practical circuit will do that, because when you have a gate, we have seen a gate will have a delay, correct? A propagation delay. So now let's think of what is the impact of, yes, what is the impact of propagation delay on these kind of circuits, because we are talking about circuits which are whose behavior we're analyzing with respect to time, and we said these are sequential circuits because they have a response which varies with the time based on their previous output and present input. That is why we call them a sequential circuit. So let us try to analyze this and just think what would have happened if this took some time to change. That is, instead of getting Q here like this, suppose there was a delay like this in the transition that is happening on Q0, which means instead of happening in sync with this, suppose that happened after a small delay of delta. Are you getting my point? It is responding to this edge, but the response takes some time. So this can happen only now after a small delay, correct? Similarly, the next response also will happen only after a small delay. The clock is applied, and only after a small delta delay, the change will happen on Q0. Is that okay to you? Have you understood the starting point? So it is like this Q is shifted slightly with respect to the clock. Take it that way. This Q looks as if it is shifted. With respect to the clock, they are not in tally. They are not what? They are not in pulling together. Am I clear on that? Yes. So now if you have understood that, in singular, not in sync now. No. So it looks as if it got delayed. Now let us talk about Q1 now. Q1 is a fellow which is supposed to respond to which clock? Q1 is supposed to respond to the rising edge of Q0. So Q0 is also, when Q0 is delayed or pulled like this, you can imagine that Q0 bar is also pulled out. So I will draw it like this. Instead of this, now Q0 is going to remain like they'll change to, let us assume that Q0 and Q0 bar are capable of changing simultaneously, though that is also not the case. So it will be like this. There is a small delay for the transition on Q0 also. So when there is a small delay for the transition on Q0, it is like Q0 bar is the clock for Q1, isn't it? Isn't it? Q0 bar is a clock for this fellow. So he's getting a clock not at this point of time, but slightly shifted. His clock itself is shifted. His clock is not in alignment with the clocking at this flip-flop. His clock is coming slightly delayed than the earlier ideal condition. And for that slightly delayed clock, this fellow will have his own delay and there will be a response time. So Q1, it will not be responding like this. Q1 will remain like this. Clock notification you got a clock only here. So with respect to that clock only, Q1 will change. And for Q1, it takes its own delay. So effectively, if you talk with respect to the original incoming clock, your Q1 is getting delayed by 2 delta, correct? Or in other words, let me pull up the figure in your textbook itself. Okay, let me pull out the figure in the textbook itself. Look at this figure. Hope you can see it. Can you see the figure? This is the this is your Anand Kumar. Okay, so this is a negative edge triggered scenario. Here is your clock, and here is your Q1. So Q1 got delayed by a small value. Hope you can see the broken lines. Q1 got delayed by a small value, and then the falling edge on Q1 is also late with respect to this. So for this late falling edge, this will be further late to respond. And it is this falling edge that causes Q3 to respond. So this is delayed further. So this will be further delayed. Are you able to catch it? Which means that whatever we expected to happen on the falling edges of the incoming clock will happen, but not at the same time as we expected, but after a delay. So as the number of stages increases, if there are more number of flip-flops, everybody will get delayed by this delta. So if there are n flip-flops, what will happen? There will be a total delay corresponding to n times the delay of one flip-flop, assuming that all flip-flops have the same inherent delay. So if every flip-flop has got a delay of, let us say, we normally write it as TPD. So if every flip-flop has got a delay called as TPD, the propagation delay, and if there are n flip-flops, then n times TPD would be the delay the last flip-flop. Do you agree? The last flip-flop will have a delay of n times TPD. Is that clear to you? Is that clear to you? Yes. So now what is the problem with this? What is the problem with this? The problem is, if you can assume that this is an interval of 1 second, okay? Imagine that you're clocking, your incoming clock which you have applied to the counter is a 1 second clock. So your clock is a 1 second clock. So every 1 second you are applying a clock. Okay, and imagine that this delay which we are talking about is a 0.5 second delay. Are you getting me? Imagine that it is a 0.5 second delay. So this whatever is supposed to happen at this falling edge on Q1 is going to happen only after 0.5 seconds, which means somewhere here only it will undergo the first transition. It was supposed to happen here, right? Instead of happening there, it is going to happen only here. Do you see a problem here? It looks as if it is responding to the rising edge, isn't it? Yes or no? This is 1 second. I said this is 1 second, and the propagation delay is 0.5 second. So number clock we applied a clock, but he is taking time, start avan. So he took time and he started up only after 0.5 seconds, which means that whatever is supposed to happen here, this transition was supposed to happen here, that happened only 0.5 seconds later. Okay, so that is with Q1. What about okay, not Q1, Q0, first flip-flop. Now what about Q1? Suppose Q1 is also a fellow with the same sluggishness, that is 0.5 second. Then he is waiting for this to happen, right? And after this has happened, only he will change. And after this has happened, and then he will have his delay of 0.5 seconds. So then only the transition will happen. So now look at this. You don't get a proper counting sequence here. You agree? You won't get a proper counting sequence here. I'll be assuming that everything is fine. And if I look at the counting sequence 0, 0, 0, 1, then 0, 1 again. Then do you see a 0, 0 again? Then a 1, 0. Then maybe 1, 1. Do you understand? The point is, by the time the last flip-flop responds, all of them are slow. So if it is a long sequence, by the time the last flip-flop responds to a clock which you applied to the first flip-flop, the first flip-flop would have got its second clock. I repeat, if it is a long sequence, by the time the last flip-flop gets its clock from the previous stage, after all these delays, by the time he gets a clock corresponding to the n-1th clock which you applied on the first flip-flop, the first flip-flop would have received its next clock. Okay, so the only way you can get around this is you have to keep your clock interval, this clock period, whatever it is, you have to keep it greater than this. This is the only way you can get around it. Isn't it? Only if you keep your clock, you should wait till the last flip-flop response. Only then you should clock again. So you have to ensure that your clocking frequency is such that this T clock is greater than n times the propagation delay of every flip-flop. Is that clear to you? T clock should be greater than n times the propagation delay of every flip-flop. Is that point clear to you? Yes or no? Yes. So suppose I have 4 flip-flops and my propagation delay, typically propagation delay is in nanoseconds, and let us assume that my propagation delay is 1 microseconds. I have a 4 flip-flop arrangements like this, okay, where I have 4 flip-flops. So if I have a 4 flip-flop, and if the propagation delay of every flip-flop is 1 microsecond, I have a total propagation delay for the last flip-flop as 4 microseconds, isn't it? At what rate can I clock? What can be my clock? This puts an upper limit or a lower limit on the clock. Upper limit on the clock or lower limit on the clock. This problem tells you that you can clock greater than a particular frequency, or that you should clock less than. You should clock at a frequency less than a particular value. Really didn't get you, madam. Okay. Let's start once again. Did you understand this point that if one flip-flop causes a delay of TPD, then the delay on the nth flip-flop will be n times TPD? I hope that is clear. What does it mean? It means that you have Q0, Q1, 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 all the Q, and the last flip-flop is the N flip-flop, okay? N-1 flip-flop to be very precise, Qn-1. So a transition which happened here due to the incoming clock has to ripple through the different stages and cause a change here. Only then it will be complete. So if every subsequent stage takes this much delay in responding to its clock, the first clock produced a valid Q0 only after 1 TPD. Then for this valid Q0, the next flip-flop will produce a valid output only after 2 TPD. So if there are n flip-flops, a valid output will be produced at the output of the n flip-flop only after n TPD, isn't it? Yes. So if that is the case, what if I don't wait? Okay, so you know that you applied clock number 1 here, and this clock number 1 will produce a valid output here only after n TPD. Did you understand that? So when can I apply the second clock here? I cannot apply it before n times TPD, isn't it? I should not. If I apply it before n times TPD, my circuit working will be wrong, because by the time this responds to clock number 1, this would have responded to clock number 2. That should not happen, isn't it? A clock number 1 here causes a change on Q1 and then ripples to a change on Q2, then ripples to a change on Q3, and so on. And to that last flip-flop, if it is to ripple a change, it takes this much time. Not ideally, practically. So by the time this after this response to this first clock only, you should ensure that the next external clock comes in. So what should be the interval between these two clocks? That is the interval of the incoming clock. That's what I wrote. That incoming clock interval should be greater than, of course, it should be greater than NTPD, isn't it? Yes, it should be greater than NTPD. Do you understand that? It has to be greater than NTPD. So now if you take a problem like this, 4 flip-flops and 1 microsecond is the delay of 1 flip-flop. So 4 microseconds is the delay that you can expect on the last flip-flop, which means my T clock has to be, this interval has to be what? Greater than 4 microseconds or less than 4 microseconds. That is the interval between the first external clock that you apply here and the second external clock. This interval should be greater than 4 microseconds or less than 4 microseconds. Definitely it has to be greater than 4 microseconds, isn't it? Only then the circuit will work properly. Otherwise, what will happen? The circuit will give you erroneous counting like this. Is that point clear? And the erroneous counting will be, if you look at this, if you analyze this carefully, the erroneous counting will be that normally it should count after 1, 0, 1, it should count 1, 0, then 1, 1, and then go back to 0, 0, isn't it? That's the way it should count. But due to this erroneous behavior, it will skip states. I'll just show you once more. It will skip states. So T clock has to be greater than 4 microseconds for this example. So if I say clock has to be greater than 4 microseconds, frequency being 1 by 4, 1 by that, you know that the frequency will have to be great. This will correspond to a clock frequency of 1 by 4 microseconds, which is, let us say, 0.25 megahertz, correct? So now tell me, the clock has to be greater than 0.25 megahertz or less than 0.25 megahertz? Clock frequency has to be greater than 4 microseconds, greater than 0.25 megahertz or less than? I want to see responses. It has to be less, isn't it? Because it's an inequality. So when you take the inverse, the inequality will go less, isn't it? Yes. So what does it mean? What does it mean? What does it mean? It means that you cannot make this circuit work faster than 250 kilohertz. I repeat, you cannot make this circuit work faster than 250 kilohertz, isn't it? When I say clock has to be less than 0.25 megahertz, it means that I cannot apply a clock which is 1 megahertz, correct? I cannot apply a clock which is less than 1 megahertz, or that's the meaning. When I say 0.25 megahertz, it means that I cannot apply a clock which is less than, which is greater than 250 kilohertz. So clock always have to be less than 250 kilohertz, which means what? Which means if I make it work at a frequency less than greater than this upper limit, it will skip states. അപ്പോൾ നമുക്ക് കള്ളത്തരം കാണിക്കണമെങ്കിൽ ഇങ്ങനെ ചെയ്താൽ മതി. കള്ളത്തരം കാണിക്കുന്നത് എങ്ങനെയാ? 4 പേര് അകത്ത് കയറി കഴിയുമ്പോൾ 2 പേരെ കയറില്ലൂ എന്ന് പറയണമെങ്കിൽ you can use this approach. Did you get my point? Because it will skip states. ഇടയ്ക്കിടയ്ക്ക് ഒന്ന് ക്ലോക്ക് കൂട്ടി കൊടുക്കുക, അപ്പോൾ it will skip states. Yes or no? Do you see a practical application? Ironically practical application, but it's not to be done. Ethics. Do you see a practical application? Yeah, അപ്പോൾ ഇന്ന് ആലോചിച്ച് നോക്കി, നമ്മൾ suppose you are measuring something based on some counting, okay? Let us say paint. Every 100 ml of paint passing through a valve causes a trigger, okay? And that trigger is getting counted. അങ്ങനെയാണെങ്കിൽ നമ്മൾ ആ കൗണ്ടറിന്റെ സ്പീഡ് ഒന്ന് കൂട്ടി കൊടുത്താൽ, ക്ലോക്ക് ചെയ്യുന്ന ഫ്രീക്വൻസി ഒന്ന് കൂട്ടി കൊടുത്തു കഴിഞ്ഞാൽ ഒരു 100 ml കയറാണ്ട് തന്നെ അയാൾ പറയും 100 ml കഴിഞ്ഞു അടുത്ത റൗണ്ടായി എന്ന് പറയും. ഇറ്റ് ഇസ് സ്കിപ്പിംഗ് സ്റ്റേറ്റ്. ഇറ്റ് ഫിനിഷസ് 1 റൗണ്ട് ആൻഡ് ഗോസ് ടു ദ നെക്സ്റ്റ് റൗണ്ട്. അപ്പോൾ ഈ 2 സ്റ്റേറ്റ് മിസ് ചെയ്തു. കൗണ്ടിങ് നടന്നില്ല, ഇൻപുട്ട് കിട്ടിയില്ല, കൗണ്ടിങ് നടന്നില്ല. ഇറ്റ് സ്കിപ്പ് ചെയ്യുമ്പോൾ നമ്മൾ ഇത് കഴിഞ്ഞിട്ട് നമ്മളത് കാണുമ്പോൾ വീൽ തിങ്ക് ദാറ്റ് ഓക്കെ അത്രയും കൗണ്ട്സ് കഴിഞ്ഞു എന്നുള്ളത്. Every time it repeats, we are under the assumption that it has gone through the previous full cycle, isn't it? That was a wrong observation. But are you clear about the problem? What is the problem? Asynchronous. Asynchronous counters can skip states. Correct? F clock. There is a maximum. There will be a maximum depending on what? What is an answer for you? There will be a upper limit on the clocking frequency that you can apply depending on what? Depending on n, the number of flip-flops, and also depending on the propagation delay of each flip-flop, depending on n and depending on the propagation delay of each flip-flop. Now we have taken a very simple assumption that all of them have the same propagation delay, and we have taken this assumption. So if that is not the case, that is if every flip-flop has got its own propagation delay, then we cannot say which state will get skipped. Some intermediate state will get skipped. There will not be a pattern. Am I clear on that? One, or if it is a case of 2 flip-flops, 3 flip-flops, we can think of we can measure each propagation delay and maybe we can compute. But when it comes to an arrangement of 64-bit counters and all, it's not that easy. Okay, so what Chella flip-flops the propagation delay for a transition from low to high will be different from the propagation delay for a transition from low to high will be different from. Yes, skipping may take place randomly if the propagation delay of the flip-flops are not identical values. These are all finer details, okay? But for S3 semester, the takeaway is that, what is the takeaway? Please chat. What is the takeaway? Please chat in the chat box in one sentence. What is the takeaway? Asynchronous counters have a problem. What is the problem? The problem is that can skip states. Okay, I would say asynchronous counters may skip states. Do you agree? Great, Leah, that's more correct. Okay, what is a in effect rule? What is a rule that I should say without saying that there will be skipping of states? What should I say? I should say you cannot clock an asynchronous circuit beyond a certain frequency. Circuit proper skip. So if the circuit should not skip a state, you should not clock it beyond a certain frequency. So skipping states is the problem. So to avoid that problem, what is the limitation that we have? You have a problem. Don't go into the problem. If you want to avoid that problem, the caution is that you should not go beyond a certain frequency. Or in other words, the speed of asynchronous circuits is limited. You take that? Limited by whom? The speed of asynchronous counters is limited. Limited by, don't just say delay, you should say the propagation delay of individual flip-flops. Okay? By the propagation delay of individual flip-flops. Yes. Is that understood? Is that understood? Yes. Now let me conclude that with a very funny observation. Very funny observation. This is a very funny observation. I'm going to write down the sequence of states for a mode 8 counter. Okay. So Q2, Q1, Q0, 0, 0, 0 is the first state. Then it goes to 0, 0, 1. It goes to 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0. 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 1, 1, 0, and 1, 1, 1. Do you agree? And then it goes back. Next is 0, 0, 0. This is how it happens, right? Tell me which of these let us assume that all the flip-flops have the identical TPD. All of them TPD are same for all the flip-flops. Okay, all of them have the same TPD. Okay, same TPD, same. Now tell me, out of these different states, which state is going to be affected maximum by this problem? Which transition is likely to be affected maximum by this problem? Which is the point at which there can be a max? Okay, I said, when I say counter state, and state of the counter means this is the state 0, this is state 1, state 2, state 3, state 4, and so on. That's what we call as the state of the counter. This is the output, okay, output point, pin, or output value, one of the bits. State means it is this 3-bit number is called as a state. So which state is going to be? Yes, Shreya, unmute yourself and explain your answer. Yes, Vishnu, you're right.
Hello, ma'am.
Yes, Shreya, go on.
Ma'am, because the propagation delay would be n into TPD. So the 7th state would be having the most delay.
Can you be more clear on that based on this what I have written here? Is there any other way of putting it across? N has got nothing to do with 7. Okay, N is not 7, N is 3 in this case, isn't it?
Yes, ma'am.
So please correlate. N TPD is correct. Here N is 3. It has got nothing to do with the value 7. So why did you pick up 7? That's my question.
Ma'am, because there are 7 states here. Because it will repeat after the 7th state. So
I would say it will repeat after every 7th state.
yeah, every 7th state.
But why is the 7th state important? Why did you pick the 7th state? Why you didn't tell me 001? NTPD and frequency for each state increases. One stage, there is only one TPD. One stage has got only one TPD. As the number of stages increases, what is increasing? The total. This is the total TPD, isn't it? Total TPD is equal to NTPD. That is increasing as the number of states increases. My question is, for the 3-state case, for the 7-state case where there are 3 flip-flops, which is the state for which this will be a biggest issue? Vishnu gave an answer. Can you explain, Vishnu?
മാം അതിൽ ലാസ്റ്റ് വരുന്നത് 7th സ്റ്റേജിൽ 111 മാക്സിമം അല്ലേ, അത് കഴിഞ്ഞിട്ട് 0 ആവുന്നു. ഇത് Q1 Q2 Q0ന്റെ കാര്യമല്ലേ, മറ്റേത് ക്ലോക്ക്.
Q1 Q എന്താ അപ്പൊ അവിടെ വരാം 7th വരാൻ കാര്യം എന്താ? എന്തുകൊണ്ട് 3rd വന്നില്ല?
മാക്സിമം അല്ലേ 111 അത് മൂന്ന് ഫ്ലിപ്പ് ഫ്ലോപ്പും യൂസ് ചെയ്യുന്നുണ്ടല്ലോ.
കറക്റ്റ്. മൂന്നിന്റെയും അവസ്ഥ മാറണം. യെസ് വിഷ്ണു പറഞ്ഞു വന്നത് തിരിഞ്ഞു മറിഞ്ഞാണെങ്കിലും യു ആർ ദയർ. ഓക്കെ, others please listen.
യൂസ് ചെയ്യുന്നത് 2 ഫ്ലിപ്പ് ഫ്ലോപ്പ് അല്ലേ?
Other, correct. So just listen, others. When the first edge comes, then the edge let us assume that it is going to happen on the falling edge. So first edge വരുമ്പോൾ there is a transition on Q0, correct? But is there a transition on Q1? Is there a transition on Q2? There is no transition. And this falling edge on Q1 is going to trigger a transition on Q1 in the next clock here. If it is a falling edge, then this transition, this 1 to 0 transition on Q0 is going to trigger a transition on Q1 also, isn't it? This transition has to trigger a transition on Q1 in that state, at that point. And in the next clock, in the 3rd clock, here you have 0 to 1 transition. So it is not a valid input for Q1. So this 0 to 1 transition on Q1 will not cause a change here. It will remain the same. See, it has to remain the same. But next time when the clock comes, there is a 1 to 0 transition here. That will cause a 1 to 0 transition here also. So if this flipping happens, then we assume that this also has to happen in the same incoming clock. This is one incoming clock's position. So in the same incoming clock, that transition also has to happen. Now, next one, aloche 0 to 1. 0 to 1 is not a 0 to 1 on Q0 is not going to change Q1, but a 1 to 0 on Q1 will change. Sorry, a 1 to 0 on Q0 will change Q1, and Q1 will transit. So this is causing a transition here. Now next, 0 to 1. 0 to 1 is a high going edge, so that will not cause a change on Q1. Q1 will remain there. Look at the next one. In this case, there is a 1 to 0 transition on Q0. Because Q0 has undergone a 1 to transition, Q0 and ഇവിടെ 1 to 0 transition വന്നുണ്ട്. Because Q0 has undergone a 1 to 0 transition, ഇവിടെ there is a high to low transition, isn't it? There is a high to low transition here. So because you gave an edge here, there was a transition here, and this transition has to cause a transition here. So this transition causes a transition here, and for ഒരു സ്റ്റേജ് കൂടെ ഉണ്ടായിരുന്നെങ്കിൽ ഇതിന്റെ ഔട്ട്പുട്ട് ഫോളോ ചെയ്യുന്നതുകൊണ്ട് ഇതിന്റെ ഔട്ട്പുട്ട് ഫോളോ ചെയ്യണം, ഇവിടുത്തെ ഔട്ട്പുട്ട് ഫോളോ ചെയ്യണം. Which means this transition on Q0 has to trigger a transition on Q1 on the same clock, and it has to cause a transition on Q2 also on the same clock. So the worst case happens when all the flip-flops have to toggle with respect to the incoming clock. That is a scenario which happens when you are at the highest count. When you are at the highest count, all of them have to go back to 0, isn't it? So which means all flip-flops will have to undergo switching before the next clock. And this transition happens in after this has happened, you take a delay of delta to make this happen, then you take a delay of delta to make this happen, only then this happens. So as far as this is concerned, the total delay is 2 delta with respect to the incoming point, incoming time, incoming clock time. So as the number of stages increases, this transition on the nth stage will happen after n delta. So this worst scenario appears when the whole system is undergoing a transition where all flip-flops have to toggle. This toggle triggers a toggle here, this toggle triggers a toggle here, and it has to go like that. Only when the last one has toggled, you have reached the state, isn't it? The next state has to be 0, 0. Upon Aluchuku, suppose you are at 1, 1, 1. After delta, if you observe the output, you would see that this is toggled, but this is at 1, 1, 0, isn't it? Because this toggle has not reached up to the second stage. Then after one more delta, if you look, this will remain a 0, and then this would have toggled. So it will be like this. Then after one more delta, if you look, this would have become 0, this would have become 0, this would also have become 0. Which means that from 1, 1, 1, we said it will immediately go back to 0, 0, 0 on the next clock. But actually it happens only after. Hello, actually it happens only after. Actually, it happens only after 3 delta, isn't it? ആദ്യത്തെ ഡെൽറ്റ കഴിയുമ്പോൾ ആദ്യത്തെ ഫ്ലിപ്പ് ഫ്ലോപ്പ് മാറി, അതിനനുസരിച്ച് രണ്ടാമത്തത് ഒരു ഡെൽറ്റയും കൂടെ കഴിയുമ്പോൾ മാറി, മൂന്നാമത്തത് മാറണമെങ്കിൽ ഈ ലാസ്റ്റ് ഫ്ലിപ്പ് ഫ്ലോപ്പ് ചേഞ്ച് ചെയ്യണമെങ്കിൽ it takes a time of delta. So on a macro scale, you have a transition from 111 to 000. But when you go down on the scale, time scale, at time interval, there is a switching happening like this. But this delta is nanosecond. On a macro scale, if you're clocking at 1 second, one second you expect the count to go from 7 to 0. But then one second ingane sambhavichittu another mara. Is that clear? Yes. Okay. Think over it, huh? You should think over it, and you should get over it. And in American. Okay. So first time kekumbo oru confusion aanu, but then it's a very simple concept. If there are dominoes ille, dominoes, you know, dominoes. Hello, you know dominoes? Is there a lot of dominoes ille ingane vekkina saana? Hello, are you all there? You know dominoes, right? Dominoes നമ്മൾ ഇങ്ങനെ അറേഞ്ച് ചെയ്തിട്ട് ആദ്യത്തെ ഡോമിനോനെ മറിച്ചിട്ട് കഴിഞ്ഞാൽ അവസാനത്തെ ഡോമിനോ എപ്പോൾ മറിഞ്ഞു വീഴും? ടക്ക് 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 ടക്ക്. It takes time, right? Hello. Imagine that you have a domino which can be flipped. Yes, ma'am. Which dominoes? Dominoes ഇല്ലേ നമ്മൾ കളിക്കുന്ന? This thing, you can see, right? കണ്ടിട്ടില്ല അത് dominoes മറിച്ചിട്ട് കളിക്കുന്ന? Yes. So അത് നമ്മൾ മറിച്ചിടുമ്പോൾ ഒന്ന് മറിഞ്ഞ് then it will take really mistake for pizza. I said it is not pizza. Yeah. Okay. So ഒന്ന് മറിഞ്ഞ് വീണിട്ട് അടുത്ത. Suppose imagine that the domino is such that when the first input comes, ഒരു liver operate ചെയ്യാന്ന് വെച്ചോ. First liver triggers this. Liver പോയി കഴിയുമ്പോൾ ഇയാൾ നൂർന്നിരിക്കുന്നു വിചാരിച്ചോ. And then next time when the liver comes only, all these will flip, isn't it? But then if they are slow, then if you keep flipping the first domino fast, then what you see in this would not be a smooth normal pattern what you would expect otherwise. നമ്മൾ മറ്റേ മൂവിയിലൊക്കെ കണ്ട പോലെ ക്രിസ്മസ് സ്റ്റോറി എന്താ പേര്, ഹോം അലോൺ, അതിലൊക്കെ ഉണ്ടായിരുന്ന പോലെ you have a series of events happening, but if the rate at which you trigger the events is faster, then your series gets disturbed. Simple. Based on how much time it takes for each event to happen. Is that clear? It's quite a natural phenomenon. Every event, if it takes time, then if you are arranging a sequence of events, the rate at which you trigger the event should be such that first trigger should be applied, allowing time for all the events to happen, and then only you should apply the next trigger so that the same series of events happen in the proper sequence. Isn't it? Simple logic. So here in digital circuits, we call it in terms of propagation delay, maximum clock, and all those things. But it's a common or a natural consequence of things when things have to happen in sequence. So to overcome this problem, we go for a kind of circuits which you might have already guessed, the kind of circuits which we call as synchronous counters. So synchronous counters will overcome the speed limitation to some extent of asynchronous counters. So this is our next discussion. So as I said, I'll run this Lido now. We'll finish this Lido, and you can take a break after that, and then we'll come back and start discussing synchronous counters. So I've started the Slido. Can you see it? It's 22823. Please join. It's 22823. Vasant, can you please respond? Are you able to get the Slido? 22823. Okay. Please join with your register number. Vishnu and Sri Priya, you can use your 2041, that number. Join with that number. Shall we start? നേഹ രാവിലെ തന്നെ ഡോമിനോസ് പിസ്സ എന്നൊക്കെ പറഞ്ഞിട്ട് എനിക്ക് വിശക്കുന്നു. I haven't had my breakfast. I think same there also, right? Yeah, so let's start. For modulo 8 counter, we need minimum dash flip-flops. Minimum. For modulo 8 counter, we need minimum how many flip-flops? There is a logarithmic equation which we all know. Yes, I don't know why somebody said 8 flip-flops. Okay, so the correct answer is what? 3. 3, isn't it? 2 to the power of 3 is 8. That is the relationship. 2 to the power of number of flip-flops equal to the maximum modulus. So, if you have understood that, for a modulo 9 counter, how many flip-flops will you need? Modulo 9 is not directly realizable. We realize modulo 9 with the help of a counter which has got more number of states, and then you use reduced modulus using that extra circuit. So if that is the case, for a modulo 9, how many flip-flops will you require minimum? Very good, very good. It's 4. So 4 will give you 16 states, 16 modulus maximum. So use that, reduce it and use it as a modulus 9. Yes. In an asynchronous counter, used to count the number of cars entering a bay, the deployed sensor's output is a momentary voltage drop when the car passes. Which bit of the counter toggles for every car entry? And what is the preferred flip-flop clock type? Okay, more time. This is in an asynchronous counter. The sensor output drops when the car passes, and that sensor output is used for counting. The correct answer is LSB. I've been telling this many times. Whenever there is an asynchronous counter, LSB bit, look at any sequence that you wrote, LSB bit toggles for every clock. Every clock. So ഓരോ കാർ എൻട്രി ചെയ്യുമ്പോൾ LSB-ലാണ് ടോഗിൾ ചെയ്യുക, എന്നിട്ട് അത് അടുത്തതിലേക്ക് റിപ്പിൾ ചെയ്യുക ചെയ്യുന്നത്. So that's a very important. I have repeated multiple number of times. This is something everybody goes wrong also. So please ensure this in your understanding. For an asynchronous counter, LSB toggles every clock. LSB, least significant bit. And the preferred clock type is negative edge trigger because it's a momentary voltage drop. And hence, the correct answer is the first one. A silly question. T flip-flops are widely available commercially, yes or no? തെറ്റിക്കരുത്, ആരും തെറ്റിക്കരുത്. I should get 100% in this. I told you in the beginning, T flip-flops are not available, so we have to convert a JK and make a T. Okay, those who have marked yes, I'm so sorry. Let's move on. The asynchronous inputs of a flip-flop are I don't understand why majority said clock is an asynchronous input. How can clock be asynchronous? Whenever you talk about synchronous or asynchronous, it is with respect to clock. With respect to clock, whether something happens together, that is the meaning, isn't it? So clock is the reference. So why do you call clock as an asynchronous input? That's wrong. Reset and clear. Our last option was set to confuse you, but many of you fell into that. Preset, clear, and clock killer. Clock is not an asynchronous input. We're talking with reference to clock. Everything with reference to clock. I hope the point is clear. Those who have gone wrong. Enable and clock. Any clock or so that is why this option is wrong. And J and K are not the asynchronous inputs. J and K are the synchronous inputs. So if we have gone through that, then you will have the answer. A table which lists the inputs required to be applied to the flip-flops inputs to make it undergo a given state transition is called. Okay, it's a 50% call. It's called the excitation table. There are 3 different tables which we discussed. Excitation table is the answer. Okay, please be clear about that. But still. This is where we are heading to now. A type of counter where all flip-flops in it are triggered simultaneously together is called I don't know why somebody answered up and somebody answered asynchronous. This is like this is an answer which I didn't want to go wrong because okay, let's see. A JK flip-flop has its J, K and clear pins tied to VCC. Note that J, K and clear, all of them are tied to VCC. When I say clear, it means clear is active high. When I say clear bar, it means clear is active low. So here clear is tied to VCC. So when a valid clock is applied, which is true. Answer എഴുതിയവർ ഒന്നുകൂടെ ഒന്ന് ആലോചിച്ച് നോക്കി. Clear is tied to VCC and clear is active high. And if clear is high, what will happen in the flip-flop? Look at the answer. If clear is high, what will happen to the flip-flop? Clear is the input, asynchronous input, which you apply to a flip-flop to set its to make its Q equal to 0. So if you keep clear high, then it cannot toggle. It has to be always 0. So this is the answer. Okay? It will not toggle at all, even if you apply clock. The basic building block, okay, block and a circuit, not big signal. The basic building block of a sequential circuit is called is dash. There's only one more question to go. 5, 3, 2, 1, 0. Okay, great. The basic building block of a sequential circuit is flip-flop. Why did somebody say latch? I can understand going wrong, but why did somebody say mux is a basic building block of a sequential circuit? Mux is the basic building block, can be the basic building block of a combinational circuit. Okay, last question. Okay. Yes, a flip-flop can be looked upon as a memory element also. That discussion we'll have in Friday class. Okay, so now let us see the leaderboard. 9076. Who is 9076? Oh, I am joking the number. Samir. Congratulations, Samir. 9076 with 1.56 as the timing. And who's 9085? Congrats.
Siddharth.
Oh, Siddharth, you're back. Okay, who's 9066? There are.
Ma'am, it's Nandita.
Okay, so there are many people on 8 out of 10. 9094 Ara. And so.
Ma'am, Tom.
Okay, I can't see it on my board. Okay, so congratulations all of you. Thank you for giving it a good attempt. It's good to see that you have scored more than, all those if you have scored more than 6, it's very good. You have been following, I understand that from your response. Okay, now we'll take a Maggie time break. Come back after 2 minutes and we'll start our discussion on synchronous counters back in the meet. So it's a 2 minutes break now. Go have a cup of coffee or a quick munch of a biscuit and come back. 9089 ആരാന്ന് പറഞ്ഞേ? Who's 9089?
Ma'am, it's Shreya.
Okay. Congrats, Shreya. And നിലവിൽ എൻ്റെ കയ്യിലുള്ള ലിസ്റ്റിൽ there are only 5 in the list. I'll send you the leaderboard to see where each one of you stand. Okay, so take a break and come back. 2 minutes. Come back with a fresh page handy. We're going to start the synchronous counters. The next most important topic. And what you're going to write in the next, some portion of what you're going to write in the next 30 minutes, you'll have to upload along with that table which you have prepared. Okay, just 2 minutes, huh? Quick 2 minutes. Okay, so let us start. What is this? Can you see the slide also now, Vasant? Can you respond? Okay. So we are going to discuss synchronous counters, but this is just an intro slide. Don't get confused with this slide. What the slide just shows is ഒരു പൂക്കളം വരച്ച് വെച്ചിട്ടില്ലേ? Okay. What is this പൂക്കളം called? What is this diagram called? What is such kind of diagrams called as? Yes, they are called as state diagram. Yes, good. So state diagram tells you what the different states are. Can somebody look into this diagram and tell me how many states are there in this diagram? Yes. So it has got 8 states. So we can call this as a modulo 8 counter, isn't it? I can call it as a modulo 8 counter. So you might see figures like this in your textbook. Don't get confused. What it means is that S0, S1, S2, S3 are the names that they have given for the state. Okay, so we have represented the states with these names using binary numbers 000, 001, 010, etc., etc. So we have represented them using the binary values of those states. Every state you have assigned a binary number. So we have been writing what inside the circle you will write it as 000 with this understanding that that is one of the states. Let us say with the name state 0. So this diagram or the diagram which we have been drawing is all the same. Now, another difference which you might see here is there is an arrow going from what state 0 to state 1, and on the arrow, can you see something like 1/0 written? 1/0. Yes. Now that is like telling that the input is 1. There is an input, a control input. The control input is 1, and there is an output also for the circuit, which is 0. So this is a circuit which has got a control input. And if you look at this table, how do you understand this table that is written there? The columns are present state, next state, and the output. Okay, and the sub column says what is the next state if x is equal to 0, and this says what is the next state if x is equal to 1. So x is what the first value on the arc is. So it is like x slash. So the first bit shown there is x. Now look at the table and see what is being shown in the table. If the present state is s, and if the value of x is a 0, what is the next state? The next state is a 0 itself, isn't it? Which means it is remaining on the same state. Do you get that? If that control it is not the clock. You're not talking about the clock. Clock is different. This is like if at all, if the clock is also applied, and then if x is equal to 0, it will not count. It will stay there. Okay, so this is like something like the enable pin. So if enable is 0, the counter will not. If enable is 0, the counter will not progress. If enable equal to 1, and if the present state is S0, and if you have applied a clock, it will go to S1. If you are in S1, it will go to S2. If you are in S2, it will go to S3, and so on. Is that point clear from this table? And that information is what is being shown there. If you are in S0, and if you are in, if the input x is equal to 0, it will loop back. It will loop back. It will loop back. Now, talking about the output. Look at the output column. Output is always 0 if x is equal to 0. So if there is no counting, this output is not there. So let us call the output as y. So y is equal to 0 if x is equal to 0. And when is y becoming 1? Only for one situation. What is that? When you transit from S7 to S0. So I can say this is like a circuit which will give an output 1 whenever the counter goes from its maximum count back to the starting point from S7 when it goes to S0, isn't it? When x is equal to 1, it goes from S7 to S0. So when you are in the present state with x is equal to 1, you're getting a 1, which means that if I have a counter with Q2, Q1, Q0 values, and if I just connect a AND gate like this and take an output from there, when will this AND gate give me high? Only when all its inputs are high, right? So this kind of an output which you derive from the counter, which you extract out of the counter, is what you call as the output in this in this state diagram. So the state diagram, and if you look into the diagram, look into every arc, there is only one arc out here. This is the point where the output is 1. For all other case, what you write below the slash is a 0, which means that is all these values. So only case where the output is a 1 is this. Okay, so this is what you call as the case where the output of your system, output y of your system, counting output alla, an extra output y of your system becomes a 1. So now this is a general representation which you might find in textbooks. So I just wanted you to become familiar with that. Now what we're going to do is the synchronous counters, and then we'll come back to all these slides. Synchronous counters. So what is a synchronous counter? A synchronous counter is the one where both flip-flops or any number of flip-flops will get clocked simultaneously. So see, clock is applied to both the flip-flops. Okay, the same clock is applied to both the flip-flops. This is the most important thing in a synchronous counter. So then the question arises, the clock is the same. After the clock transitions, clock was rippling and you had kept t different, right? T was kept on 1 in the asynchronous flip-flops. Always t were 1. So now if clock is same, then you have to do something on t to make the counter work as a counter. So that is what you have to design. So this you can achieve by a systematic procedure. First we'll go through the design and then we'll see why this happens. So the design process would be, first you have to write the present state column, just we saw in the PPT. Then you'll have to write a next state column. Okay, so present state and next state. So present state is the value on Q1 and Q0 which we want, which we have, and this the new state is Q1, Q0, which you want. This let us say it is at n, so this is n plus 1. Or you can use some other symbol like Q1 dash, Q0 dash, but that will be confusing. So what you can do is you can just write n here and n plus 1 there, with the understanding between us that this is the present state and this is the next state. Hope you have done that in your notebook. Okay, now if you remember this table, what is this table called? What is this table of T flip-flop called? It is called the excitation table, isn't it? And what does the excitation table tell us? If the present state of the T flip-flop is given, and if you want this as the next state, you should apply T equal to 0. So this I'm going to copy here. Okay, I'm going to write it here. Present state, next state, and T. This is what? This is the excitation table of T flip-flop. So write down the excitation table of T flip-flop. Copy it if you have it with you. Otherwise, present state 0, next state 0, you have to keep for a T 0. So if the present state is 0 and if you want the next state as a 1, you have to keep T as 1. That is, you have to make it toggle. If the present state is a 1 and if you want the next state as a 0, you have to make T1. The present state is 1 and if you want a next state of 1, you have to keep T equal to 0. So it means if you want to make these transition happen in your circuit, these are the values of T that you should apply in a single T flip-flop. So now what we are going to do is, based on this information and based on our present state and next state requirement, I am going to write down what value of T1 and T0 will give me the wanted transition. I repeat, based on this knowledge, I'm going to prepare a table which will tell me what value should I apply on T1 and what value should I apply on T0 so that my counter undergoes a given transition. So suppose I want my counter to count like this: 0, 1, 3. Okay, we'll go straight. 0, 1, 2, 3. Suppose I want the counter to go this counting: 0, 1, 2, 3. Okay, since it is 2 flip-flops, I can get only 4 states. So let us say we want to do up counting. What are we designing? We're designing up counting, but synchronous. So if this is the counting sequence that I want, what does it translate to in the table? The present state is a 0. That corresponds to this value, 0. I want the next state as what? I want the next state as 0, 1. Is this clear to all of you? Have you all understood this, of what I wrote here? Yes or no? Okay. So now if the present state is 1, here. What do I want the counter to go to? I want the counter to go to 2, isn't it? Yes. So binary number, I should write 1, 0. Let's complete it. All of you are doing this, right? Now, if the present state is 1, 0, I want the counter to go to 3, that is 1, 1. And what do I want my counter to go? If the present state is 1, 1, the last one, that is state 3, 3 written in binary is 1, 1. So I want the counter to go to 0, 0. So this is what I want my counter to do. Now, what am I designing? This is what I'm going to design. Design the required T1 and T0, which will make this happen. So to understand what is the required T1 and T0 which will make it happen, first look at just Q1, Q1n and Q1n plus 1. What is it? This is Q. If this is Qn, this is Qn plus 1 for a particular T flip-flop. So you have to look at this column and this column. Okay, look at these two, this and this. So it is undergoing from 0, it has to stay on 0. So it is like this row, correct? So what value of T will give me that? 0, isn't it? If the present state is a 0, and if I want the flip-flop to have its next state also as a 0, the T of that flip-flop should be 0, correct? So where do I write that 0? I write it here. Looking at this 0 and this 0, I'm writing this 0. Is that clear? This 0 should remain as a 0. And what value? And since it is on Q1, it is T1 who is going to control it. So what value should I apply on T1 so that this will happen in the circuit? From the excitation table of T1, I know T1 of 0 will make it happen. So if you have understood this, tell me, what should I write here? I want more responses. What should I write under T0 in the first row? In the first row, what should I write under T0? In the first row, what should I write under T0? One, isn't it? Why? Because there is a transition from, I'm looking at this, the hash cases. Okay, there is a transition from 0 to 1. And to have a transition from 0 to 1, look into the excitation table of T, I need a T value of 1. So that is what I'll write here. So can you now complete the table? To write the first column, you should look at the first and the second columns here. Sorry, third column here. To write the last column, I should be looking at the Q0 positions. So look into the positions, 0 and transiting to 1. It has to be 1. 1 transiting to 0. It has to be 1. Next line. 1 transiting to 1. It has to be 0. And for a 0 transiting to 1, it has to be 1. 1 transiting to 0, 1. 1 transiting to 0, 1. Did you all get this? Great. So what is it that you got just now? What you got is, in this circuit, the question which I asked is, how will I control T1 and T0? For what? To get this kind of transitions. So here is the answer. Now I have to analyze this answer. I have to control T1 so that this is what I apply on T1 on every clock. Every clock, T1, if T1 gets 0, first clock T1 should be 0. Second clock if T1 gets a 1. Third clock if T1 gets a 0. Fourth clock if T1 gets a 1. If that happens on T1, if I can make it happen on T1, then its output, Q1, will behave like this. Are you clear on that? So I should make an arrangement which will cause this to come properly in that order on T1. And what is it that you want on T0? What should I want? What do I want on T0? If I want this transition to happen on T0, the table tells me that don't do anything on T0, just keep it high, always high. Is that understood? Is that understood? Yes. So this answer is now solved. I'm going to connect it to high, or I'm going to make it high. Great. Looks very much like the asynchronous counter. But then T1, I have to find out. To do that, so this, I hope everybody is clear. T0 has to be 1. The answer to this question mark is that T0 has to be 1. Is that clear? Now, to find the answer to T1, what should I do on T1? so that how do I control T1 so that this sequence appears when this transition is required? For that, what you have to do is you have to prepare a table where your input is this and you have this output. Now, chala, let's understand it very clearly. The scenario in the circuit is you have a present state Q1, Q0 as 0, 0. If the present state is 0, you want your system to go to 0, 1. And for that system to go to 0, 1, I want T1 to be 0. So what is controlling what is going to decide my T1? The only thing that can decide my T1 is these two bits, the present Q1 and Q0. So for this value of Q1 and Q0, I need T1 equal to 0. For this value of Q1 and Q0, the present value, I need this. So now ignore this, and for this, you draw a K-map. Okay, so you'll write Q1, you're writing this, okay? You're writing Q1N, not this. Be clear about this Q1 and this Q0. So this is cell 0101. What do I map? I bring this into this K-map, T1. This is the K-map which I prepare for T1. So now fill it up, 0, 0, which is this cell. What do I want on T1? I want a 0. So of course you can write this because it's only a gate. Now 0, 1, what do I want? What should I write here? What T1 do I want? 1, 1, 0, this row, 0. And last one, 1, 1, here, 1. Okay, did you understand how I mapped from the table to the K-map? So what did I do? I am trying to find out how I can control T1 based on the present state. So present state is what I have from Q0 and from Q1. So I am going to write T1 as a function of the present Q1 and the present Q0. Present Q1 and the present, I'm writing N inside. It's understood that it is only the present state. So I am trying to control T1 as a function of the present Q1 and the present Q0. So what is this function? This is where you need your knowledge of K-map. So what is the function? The function is what is the expression for T1 from the K-map? Q0 bar, isn't it? So T1 is equal to Q0 bar. Have you all understood this? T1 is equal to Q0 bar. So does that answer our query? What was our query? What should I apply on T0? What should I apply on T1 so that I get these transitions? Did you understand? What did I apply? I have not applied it, but what should I apply? From the design, I understand that you take a connection from Q0 bar, isn't it? You take a connection from Q0 bar and give it as T1, magic. So you have a Q0, you have Q0 bar. No bar? Oh, I'm sorry, no bar, sorry. It is Q0. Thank you, Samir. It's Q0, I'm sorry. No, I'm sorry. No bar. It is Q0. Very sorry. That was not a planned mistake. It was an unplanned mistake. Okay, so T1 equal to Q0. I'm very sorry. T1 equal to Q0. Do you understand? So what is it that I'm seeing now? I have to make a connection to T1 from Q0. So now look at this. In the asynchronous flip-flops, you were cascading Q0 with the clock. Here clock is separate. Clock is direct. So you are making a connection like this. Connect this to T1. Have you understood this? So what are the two connections? From the table, obviously I saw that T0 is a 1. So I connected it there, T0, 1, permanent. And by reducing the table, I saw that my T1 is dependent on Q0 direct. So I've connected Q0. Now if you analyze the circuit, you will see that this circuit is going to give you this counting sequence. Okay. So reiterate the steps. You are asked to design a counter like this. I write down the excitation table. I decided to use a T flip-flop. I can use any flip-flop. But let us start with T flip-flop. Later in the next classes, I'll tell you how to do it with JK flip-flop and other types of flip-flops. So let us assume that we are going to use T flip-flop. If nothing is mentioned in the design, then T flip-flop is easiest, but practically T flip-flops are not available commercially. So we'll have to implement a T using JK and then use it. Okay, so this is your excitation for the T. Then the design part is this. Write down the present state and the next state that you want in the counting sequence. Look into the counting sequence given and write down the present state and next state. Write down the design equation, design values of T1 and design values of T0. How do you write it down? Look into the value of Q1 and the next state Q1. So it is 0, transiting to a 0. Look here, what do I need as T if 0 has to remain on 0 for the excitation table? It is a 0. So you write 0 here. Again, next, look into Q0. The present Q0 is 0. I want the Q0 to become 1 on the clock, on the next clock, like this. So what do? I look into the excitation table and I find out the row which corresponds to that. For a 0 to 1 transition on the T flip-flop, I must provide a T equal to 1. So write down T, that particular T equal to 1. Likewise, you fill up this table, translate that into a K-map. How do I translate that? While translating that, you have to use this input, this section as the K-map inputs, variables, and write down the K-map for T1, and sometimes you'll have to write down the K-map for T0 also. So this is an example where T0 is very straight, very clean. So write down the expression, reduce the expression, get the expression, and make the connection accordingly. So what did we do? We just designed 0, 1, 2, 3 counter. Okay, 0, 1, 2, 3 counter. So suppose now I ask you, please make a counter which goes from 0 to 2 to 1 and then come to 3 and then come back to 1. A twist. I want you to make a counter which will go from state 0 to 2 to 1 to 3 and then come back. A change in order. Use T flip-flop. Use T flip-flop. Let's try present state, next state. Correct? There are four states, isn't it? So 4 states. So starting point is 4 states. So the question arises, how many flip-flops? Answer me, how many flip-flops? How many flip-flops? 2. Okay, let's write it as Q1, Q0. Q1, Q0. Present state I'll write as Q1n. Next state I'll write it as Q1, Qn, n plus 1, n plus 1. Draw a simple line here. And this is to be demarcated from my control signals. What are the 2 control signals that I'll need? Design for what? Design for the set, you have to use T flip-flops. So you have to design for one flip-flop for the first bit and the second flip-flop, T0. Is this clear? This is how you arrive at the table. How you fix the number of values here. How many bits. This is how you fix it. And then you fix this. If it is JK flip-flop, then you will have to write 2 values, J1 value and a K1 value, J0 value and a K0 value. Okay, so T flip-flop, it's very straightforward. Now let us fill it up. So 0 is my first state. I'll write down all the states in order, 0, 0, 0, 1, 1, 0, 1, 1. Assuming that the present state is 0, where do I want the system to go? I want it to go to, come on, I want it to go to 2, isn't it? So I should write 2 here. 2 in binary is 1, 0. So this is where your conversion from decimal to binary comes in, the first module. So you wrote 2. Now, 0, 1. 0, 1 means 1. 0, 1 should go to which value? From state 1, it should go to state 3. So state 3 is 1, 1. Okay, next. Present state 1, 0 angular. So here, where should it go? It should go to 1. So what do I write? 0, 1. Now, present state 3, where should it go to? According to the timing state diagram, it should go to 0, 0. So this is done, right? First left side is done. Now fill up T1, T0. For T1, T0, write down the excitation table if you don't remember the excitation table. So write down the excitation table here and accordingly you fill it up. Or if you can remember the excitation table of a T flip-flop, that's great. You should develop that. You should write down the table. Okay, you should write down the table. Excitation table of the flip-flop which you chose of T flip-flop is our example. So present state, next state, and the required T. So fill it up. You have to fill it up. Now let's do this. I want a transition on Q1 from 0 to 1. So 1, 0 to 0, so 0, 0 to 1, so 1, 1 to 1, so 0, 1 to 0, 1, 0 to 1, 1, 1 to 0, 1, 1 to 0, 1. Funny? So this case also, I see that there is a silly example of T1 becoming 1 always, correct? Looking into the output, I understand that I can keep my T1 always as 1. And what about my T0? There is a transition. So T0, you go do it on a K-map. What do you put on the K-map? This column you put on the K-map. So you write a Q1 here and a Q0 here. So 0, 0, T0, this is for T0. So 0, 0, this is what I'm going to map. So 0, 0 will come here. 0, 1 will come here. 1, 0 is a 1. It will go there. 1, 1. Okay. Be clear on this. Q1, Q0, 0, 0. This is this. Correct? Q1, Q0, 0, 1, 0, 1, Q1, Q0. The value I need is a 0. Don't write it blindly. 1, 0, 1, 0, it is 1, 0. Q1, 1, Q0. So don't write it blindly. 1, 0. The value I need is a 1. 1, 1. The value I need on this is a 1. So it comes here. So do I have a pair here? Pair, remember? K-map, pair. A pair. And the pair is Q1. So T0 is equal to Q1. So now do you see a twist in the circuit? Do you see a difference in the circuit compared to the previous circuit? So what you have to do is you have to draw the circuit, and this sheet you have to upload. Draw the circuit. You have derived the circuit. Now just draw the circuit and upload it. And on that same page, you have that first this which you did for 8-bit sequence, right? What we did before break. So that and this. All you have to do is draw the corresponding circuit. Draw the corresponding circuit according to this design expression. Draw the circuit and upload. So when you draw the circuit, make sure that you mark your flip-flops properly, FF0, FF1, etc., and also your T1, T0, etc., following the order which you have been doing, and also the clock, because it's synchronous, you have to properly show the clock and all those things. Make sure that everything is correct on the diagram. Mark your MSB, LSB, where do you take the output, what do you do to the clock, all those things. The figure should be complete. Okay. So it's not a very hectic work. You have done it. Only thing is just draw the circuit. Will you do it, all of you? Yes. So I'll post a classroom work in the classroom assignment kind of work in the classroom. Please do it today itself. I repeat, please do it today itself. Okay, so if there are doubts, you can stay back. Otherwise, we'll call it a day. Hope you have understood the concepts which we discussed today. Please try to solidify it today itself, because otherwise it will go straight. Because I have discussed very important concepts today. Very important. Okay. So if there are doubts, you can stay, otherwise you can leave. Thank you for your patience and thank you for participating in this video. Thank you. If there is any doubt, you can stay back or you can come back to me, or else you can leave.